In 1609, Johannes Kepler published his first law of planetary motion. The Earth orbits the Sun in an ellipse, closest at one point, farthest at another. The hottest season falls at one end, the coldest at the other. 9000 BC. An ancient Indian astronomy text had already described it. The text contains 3 separate parameters that should be completely unrelated. All 3 point to the same date, 12,000 BC. The probability of 3 independent astronomical values from a single chapter accidentally converging on the same prehistoric epoch is vanishingly small. The text is the Surya Siddhanta. It has been translated, analyzed, and dated for over 150 years. Its deepest layer has never been properly acknowledged. Start with the obliquity. The Earth's obliquity is the tilt of its axis. It is not constant. It oscillates over a 41,000-year cycle, swinging between approximately 22.1 degrees and 24.5 degrees. The change is roughly 1/100th of a degree per century, and it is precisely calculable at any point in the past, using models developed by Jacques Laskar and the Paris Observatory. The Surya Siddhanta states that the obliquity of the Earth is 24 degrees. 24 degrees was the actual obliquity of the Earth around 12,000 BC, and again around 3000 BC. In 580 AD, the date the text is most commonly assigned to, it was 23.5 degrees. The discrepancy is not small. For a text that contains detailed trigonometric tables, sine functions, and methods for constructing precision astronomical instruments, recording the wrong tilt by half a degree is not a minor slip. It is evidence that the number came from somewhere else. Now the second parameter. The Surya Siddhanta, in chapter 12, states that there are 2 pole stars, one near the north celestial pole, one near the south celestial pole, both visible on the horizon from the equator. Today, we have one pole star, Polaris, near the north celestial pole. There is no bright star near the south celestial pole. This has been the case for thousands of years. If the Surya Siddhanta was written in 580 AD, its authors were describing something that did not exist in their sky. The Earth's axis precesses, tracing a circle against the background stars over approximately 26,000 years. As it moves, different stars take their turn near the celestial poles. Researcher Nilesh Oak and astronomer Rupa Bhatti, in research presented at Oxford University in 2018, calculated when 2 bright stars simultaneously occupied both poles. Around 12,000 BC, the north celestial pole pointed near the star Abhijit, known in Western astronomy as Vega, one of the brightest stars in the sky. At the same time, the south celestial pole pointed near Agastya, known as Canopus, the second brightest star in the entire night sky. 2 brilliant pole stars, one at each pole, visible simultaneously. This configuration does not repeat casually. Oak tested the calculation back 300,000 years. This specific pairing of Abhijit and Agastya as simultaneous pole stars occurs only once within that entire span, around 12,000 BC. Now the third parameter. In the same chapter, the Surya Siddhanta describes the relationship between the Earth's seasons and its orbital position relative to the Sun. The Earth's orbit is not a perfect circle. It is an ellipse. At one point in its orbit, the Earth is closest to the Sun. This is called periapsis. At the opposite point, it is farthest from the Sun. This is called apoapsis. The Surya Siddhanta states that the peak of Hemanta Ritu, the Indian winter season, coincides with apoapsis, and the peak of Grishma Ritu, the Indian summer season, coincides with periapsis. This is a statement about orbital mechanics. The Earth is closest to the Sun during the hottest season and farthest during the coldest. And this relationship is not fixed. The point of periapsis shifts slowly over time, a phenomenon known as apsidal precession. Today, periapsis falls in January, during the northern hemisphere's winter, not its summer. The Surya Siddhanta's description does not match the modern sky, but it matches 12,000 BC precisely. At that epoch, periapsis aligned with the peak of Grishma, and apoapsis aligned with the peak of Hemanta, exactly as the text describes, down to the day within the 2-month season window. This is where the implications become extraordinary, because what the Surya Siddhanta is describing, an elliptical orbit with the Sun at one focus, a closest approach and a farthest point, and a relationship between orbital position and seasonal intensity, is Kepler's first law of planetary motion. Johannes Kepler published it in 1609 AD. The Surya Siddhanta encoded it in a verse that describes the sky of 12,000 BC. 3 independent parameters from a single chapter: the obliquity at 24 degrees, 2 simultaneous pole stars, the alignment of apsides with specific seasons, each one independently datable, each one pointing to approximately 12,000 BC. Now return to the history of how this text was dated. In 1860, an American missionary named Ebenezer Burgess published the first major English translation of the Surya Siddhanta. He compared the positions assigned to the 27 nakshatras, the reference stars of Indian astronomy, against their modern positions. Accounting for precession, he arrived at a date of approximately 580 AD, a 1,500-year-old text. Respectable, he conceded, but nothing extraordinary. Then Burgess encountered the obliquity problem. The text stated 24 degrees. In 580 AD, the actual obliquity was 23.5 degrees. For a document containing precision sign tables and detailed instrumentation chapters, that discrepancy was inexplicable. Burgess wrote in his commentary that the text's entire chapter on the construction of astronomical instruments was nothing but talk on paper. If these astronomers had actually used such instruments, they would have measured 23.5 degrees. He was certain the text was wrong. He never considered the possibility that the text was right about a different time. The mainstream date of 580 AD, the date that appears in every textbook, the date that shapes every conventional discussion of Indian astronomy, is derived from one parameter: the longitudes Burgess checked. That dating is not wrong. It simply reflects the most recent update to the text. The Surya Siddhanta is not a document frozen in a single era. It is a layered text, a living repository that was updated over millennia as observations were refined and astronomical knowledge accumulated. Other researchers have found additional layers. Dr. Anil Narayana, a former scientist at the Indian Space Research Organization, analyzed the celestial latitudes of the nakshatras, a more complex calculation than the longitudes Burgess used. His analysis, conducted without any preconceived date in mind, pointed to 7,500 BC. John Playfair, the Scottish mathematician, examined the Surya Siddhanta's equation of the Sun, its formula for predicting the Sun's position, as early as the 1700s. He found that the equation was most accurate for approximately 4,300 BC. A more recent analysis refines this to 5,300 BC. A speculative but plausible fourth layer corresponds to the second instance when obliquity equaled 24 degrees, around 2,900 BC. And the nakshatra longitudes that Burgess used point to 580 AD. 5 potential layers: 12,000 BC, 7,500 BC, 5,300 BC, 2,900 BC, 580 AD, each derived from different parameters within the same 500-verse text, each testable, each pointing to a different epoch of astronomical observation. And only about 10 of the 500 verses have been analyzed this way. 490 verses remain unexplored. Burgess looked at the Surya Siddhanta and saw a 1,500-year-old text with a 24-degree error. He concluded that the astronomers who wrote it were incompetent. He was looking at a 12,000-year-old measurement and calling it a mistake. The obliquity models are published. The precession calculations are reproducible. The apsidal alignment is verifiable. The verses in the critical edition, everything Burgess needed to reach a different conclusion, was available to him. He simply never considered the possibility that they were better astronomers than he assumed. If you want to support deeper research and found this journey as fascinating as we did, subscribe to Awakened Epochs for more.